other people. There we go. It's okay. I would also like to thank all the people involved in the development and implementation of this workshop, starting by all the members of the GCI, particularly our educational and outreach coordinator, Alicia, who was in charge of organizing this workshop. I will also like to thank Jasmine from McGill GCI, who's going to be talking about how to bring green chemistry to your campus as a grad student or maybe as an undergrad student. And finally, of course, Juliana and all the Beyond Benign team for being strong supporters of our U of T GCI and for funding this initiative as well. So we're very thankful and honored to have Beyond Benign here in the form of Juliana. So with that said, I would like to formally introduce Juliana, Dr. Juliana Vidal, who is an amazing human being. And she's also a very good green chemist. Okay, she has extensive knowledge on green chemistry throughout her degrees, bachelor's, master's, PhD, and also into her postdoc. I think she's going to be talking a little bit about that work today. And now she is the program manager at Beyond Benign. So please thank Juliana for being here. And yeah, the floor is yours.
Everyone. Thank you, everyone online. It's a pleasure to meet you. I'm Juliana. Nice to meet all of you. We're going to interact in these hours of the workshop, so I'm happy to be here. So I'm from Brazil originally, and I discovered green chemistry whenever I was reading an environmental chemistry book, and I was like, whoa, I could see the light bulb like lighting up in my head, and I'm like, this is what I want to do. So I basically moved countries and everything to study what I want to study, which is green chemistry, and do this. So I did my bachelor's and my master's in Brazil, and I tried to do as much as green chemistry as possible there. So we're trying to get silver residues and valorize them and make them things that people could use back in the labs, or even like metallic silver. I did a ring of metallic silver from the silver that I recovered. It was pretty cool. So I did my PhD at Memorial University of Newfoundland, Canada, all the way on the right. And then I came to McGill to do my postdoc with Audrey Moores, and we're working with crabs and how we can valorize these residues. So throughout my studies, I really saw the necessity of like how we communicate our science, how we talk to people. Sometimes we're speaking different languages, even though we're trying to speak English in my case. And also the need of actually teaching people about chemistry, about green chemistry. The way I see it, green chemistry can be a very simple thing. We can do very simple actions every day in our labs, in our homes, and apply green chemistry, but it can also be complicated in the way you look at it. So if you're talking about metrics, if you're talking about comparison, that could be a complicated thing. But the thing is, we do our best, and we just keep going, and we know we're doing the best we can do to achieve a more sustainable future. So this is me. I've been working with Beyond Benign, by the way, since 2019. I was doing voluntary work, and then I was their communications intern, and now I'm working full time with them since I finished my postdoc. So this is my story. Today I was trying to make this as interactive as possible. So there's a thing that I discovered called menti.com. And you can actually go with your cell phones and type this code, and you have access to the interactive part of the webinar. So like, since we're all here, I know we have a little map there. So I'm gonna show you. This is the interactive part. Great, you see some green slides like this one in your cell phone. And then basically you can pin where you're joining us from, just to start the conversation. I know a lot of us are from here, but a lot of people are like in different countries, everywhere in the world. So we'll be able, hopefully, to see the pins. Are you submitting the pins? Question mark. Do you see them? Do I need to refresh the page? Yes, I see them. This is awesome. Okay, just so we can start the conversation, but like we're gonna use this Mentimeter a lot today, just so we can start getting our opinions and things and make sure all the people interact together. So yes, this is great. And we have 17 people doing things. Awesome. There's a person all the way down there. Thank you for joining us, everyone. So yes, so see, a lot of people everywhere doing things. So thank you. So this is gonna live there, and then you can have access to this part throughout the workshop. The reasons why I decided to do green chemistry too, and the light bulb went on in my head was because all the time when I was trying to talk to people, like normal human beings, what do you do? And I'd say, I'm a chemist. People would do one of these three things. They would ask me if I explode things, and I'm like, yay. If I was just like the Breaking Bad guy in that series, I'm like, no. Or they would just look at me and expect something else to happen. I'm like, no, this is what I do. So I think we can all agree there's like chemophobia, and people can be very scared of chemicals, even though we know chemicals are everywhere. And if you can look, you can even see like products that are 100% chemical free. And some people are like, yay, this is great. So I think we can all agree. And that was one of the motivations that brought me into the green chemistry world. Also, I understand, and I think we've all seen a lot of like chemical accidents happening all over the world. These are only two examples that happened in Japan and also India that were very like killed a lot of people because people didn't have the responsibility of what they were doing. So I think we need to be aware of this when we're doing everything that we do in the lab. We have a big power and we have a big responsibility. So to start, I just wanted to check, how do you feel about green chemistry? So basically, I wanted you to rate your green chemistry knowledge in the green chemistry principles, in metrics, and also in the green chemistry resource. So we have a scale from tell me, teach me everything, to call me John Warner, which is the co-founder of green chemistry, for us to know how we're gonna approach this, how fast we're gonna go in terms of definitions and things. So if you could share, okay, I see it. Good, so we have green chemistry principles, we have 5, metrics 3.6, and okay. Oh, good, thank you so much. I need to give you a time to do this because I want to go. Okay, awesome. So I think you're being very humble, by the way. Just want to say this. So as I mentioned, we have a big responsibility as chemists, and we need to embrace that, I feel. And this is a quote from John saying that the moment that we put the pencil to a paper, this is the moment that we're making this change, that we're impacting human health and the environment. And this is when we need to start thinking about green chemistry, about what we're going to do. So we are very responsible for all these things, and let's embrace this power of smart molecular design. So an example is, this is my PhD work. We're trying to, I was working with a material called biochar, and we're trying to insert biochar in polymers and make them stronger. So I was having fun in the lab doing all of these videos. So the first one is like the main polymer, and the other one was the polymer with biochar, so you can see the difference in the material properties. And like whenever I was going through and assessing this material, I was going through the things we do, like solubility, melting point, tensile strength, modulus, but I was also worried about the toxicity of this material. Like what was the effect of this material in human health and the environment, and also the environmental impact. When this thing goes to the environment, what's going to happen? So these are things that as chemists, we also need to be aware of, and it's not very standard nowadays. So for those of you who are not in the 10 of the scale of John Warner of green chemistry, this is what green chemistry is all about. It is the idea of designing process products that minimize, or hopefully, ideally, eliminate the use and also generation of hazardous substances. So the way I see green chemistry is a place that we can change the public's perspective about what chemistry is also profitable because you don't have to deal with the waste that's generated after. Also, you have all these legislations going on now, and then companies, they have to deal with that. So green chemistry gets this problem at the very beginning, and it's also increasing the market size. So whenever we have the risk of something going wrong in the lab or also in the industry, we say that this risk is associated with the hazard that the thing we're dealing with has, and also to the exposure. So what we usually do, we use gloves, lab coats, goggles to minimize the exposure that we have to these things, and therefore minimizing the risk. But the idea of the green chemistry is to minimize the risk by minimizing the hazard. So even when I have a spill, a leak, an accident, the risk is low because the hazard of the thing that I'm using is low. So this is the approach we use. And also, to practice that, these two guys, in 1998, they published the 12 Principles of Green Chemistry. And these are actually tools of how we can achieve this, how we can still have the benefits of chemistry, but in a way that's safer for human health and environment. So I'm gonna leave this here, but you have an activity to choose, and I thought you could choose more, but you can choose one. And I know you have to look at them holistic, but one principle that you would like, or you like incorporate a lot in your research. So I'm gonna leave this here because we have from 1 to 12 in the Mentimeter thing. So if you could choose the one that you're like most worried about and you think makes more sense to you, just gonna give it a couple of seconds because we have a lot of principles. And I'm gonna go to the thing now, just to see. Okay, it's principle number 7, renewable feedstocks. This is the biggest one. Okay, waste prevention going up. This is very like, it's like watching TV. Okay, cool. So I think the principle number 7 is the one that people are most worried about. Okay, number 3 is going bananas now too. Okay, let's go number 7. Cool. So yeah, so so a lot of people are using renewable feedstocks and worry about that. Makes sense. Also, waste prevention. I think I used a lot of, like my work, my PhD and postdoc was a lot of renewable feedstocks work, but also waste prevention, I think is one of the makes most sense to me. So awesome. So for those of you who have seen this, these are the UN SDGs. They are also another framework created by the UN where we can reach a sustainable future. And green chemistry is a tool for us to actually achieve a sustainable future and achieve the United Nations Sustainable Development Goals. The idea is that we're going to achieve them by 2030. But the idea is that this framework exists, it's there, we're doing it, we're striving for it. And to me, that's enough. So as I said, we're going to talk a lot about in this workshop about design and how we can get things to be sustainable and be more benign at the very molecular level. So some things that we need to think about when we're doing and applying green chemistry is like the beginning of the material. What is this product made? From what? What's going to generate? Are there any byproducts? And also what's going to happen with this product after use? So green chemistry allows us to do that and address this problem at the very beginning. So why we need that? Because we're always generating, creating, dealing with molecules all the time. Chemistry is life. So these are some numbers that show us like how we need and what we need to do this molecular design. And this is like the numbers that, like the last number that was in the molecules of the Environmental Protection Agency of the US. So we need to be generating and producing molecules that are benign to human health and to all of us that are in the planet. Also, if you haven't seen this, this is a graphic from Compound Chem. Andrew, he's an amazing person. He does super cool graphics about science communication. And this is showing us like the elements that are endangered. And then it can end up in a couple of years. So 44 of these elements will face supply limitation, and green chemistry can also help this by using renewable feedstocks and by maximizing the resource efficiency through recycling and through reusing the products that we made. So one example is detergents. So we had this TPPS that was created in the 50s and 60s, and people started to use it, and then they noticed that they had this huge problem with foam in rivers and streams. By studying things, they discovered that if you just like use a longer chain, this problem is solved. And actually, this product has a higher biodegradation and is more benign to the environment. So like these are examples of what us chemists can do, simple things that I mentioned in the beginning that you can do to apply green chemistry. So this is like, if you go to this textbook, Lancaster Green Chemistry and Introductory Text, these like a few examples of what you can do to increase the biodegradability of your products that you go in the lab and you make to make sure that they're going to be more benign to the environment. So there are rules for that things that we can apply. So also, this is kind of the difference between a chemist that's not trained in green chemistry, a green chemist, and also the sustainability impacts that these people have in the planet. So I'm not saying here that the traditional chemist, he's like, I'm gonna produce things that are bad to human health. Let's go. What I'm saying is they don't have the skills and tools to do so. So this is basically like the difference between what a green chemist can do and the materials they use and the process they can make and the products that can generate it and the impacts in global warming and also in the synthetic steps that these people can do. So these slides are going to be available to you. You can take a look at more because I know there's a lot of words happening, but this is the main idea. We make a difference, and this is like the sustainability impacts that we can do by thinking about the design. Also, I don't know if you heard a lot about like sustainable chemistry, circular chemistry, a lot of different concepts and ideas. And the way I see it is like green chemistry is the foundation, and we're going to see a lot of different approaches for these to achieve a more sustainable world. Like people are thinking about this. So the idea is like green chemistry is the how we can do it, how we can achieve the what's, like a circular economy, sustainable chemistry, sustainability, and the whys also, which is like climate change, environmental challenges, the societal challenges that we have. So to me, green chemistry is how we can make all of this. All good? I'm speaking too fast. Can I get a nod? Okay, thank you. Also, I think this is one of my last slides. I don't know if I'm good on time, but the idea is that let's try to be diverse. Let's get all of the chemists involved that you could. You know, I think diversity and including all scientists from different backgrounds. I was talking with Francisco. He was like, I'm a physical chemist. And like, green chemistry is interdisciplinary. So like we all need people from different backgrounds and things, and it's not because you do one thing that you can do another. The beauty of green chemistry is very interdisciplinary. I work with polymers and catalysis and a bunch of things in my PhD, my comprehensive exam. I was like dying, but the idea is like we need this for green chemistry to continue being what it is, and we need all scientists in the world striving to achieve a more sustainable future. So let's embrace this diversity and let's embrace all backgrounds and let's go do it. Okay. All good. Let's take a breath. So far so good. Do we have any questions at this part? How are we feeling? Thumbs up. All good. So we're gonna go into metrics right now, which are a little bit how we can assess the greenness of a thing. Basically, I'm in the lab. I made this. Is it green? Is it not? What do I do with it? So an activity for us to think about things. Whenever you're designing a new material, are you considering any of the options that you have in your screen or not? None of them. All of them. Oh, I considered this one more. I considered that one more. So let's just see if people are considering, okay, the fonts are very small. I'm sorry, guys. But if they're considering the potential environmental, health, or society impacts of their research. Okay, thank you. The toxicity of this product if it gets released to the environment. How is sustainable is the manufacture of these certain materials? Is this coming from bio-based things? Is this coming from a petroleum-based thing? Okay. None of these questions are, okay, good, we're here for this. And all of the questions. Okay, so we have people thinking about materials and design here, which is great. And the numbers keep increasing. Awesome, thank you. A lot of numbers, okay. 8. Good, thank you. So, okay, people are thinking about their design, which is great. And this is what the metrics are here for. So, one concept that we have in green chemistry is called atom economy. This was actually created a long time ago, and it was like the idea was to measure the efficiency of a chemical reaction And then the green chemists, they thought, okay, this is a really good thing that we can use to see how many atoms of my product, of my starting material, they were actually incorporated in my product, of how many became like byproduct. So like if I'm here, if I'm in the lab, if I'm designing something, why am I going to choose a route that I know that's going to generate more waste than a route that's not going to generate any waste? So this is kind of the concept of the atom economy. That's the formula. So we get the molecular weight of your desired material, divide by the molecular weight of your starting material, multiply by 100. The problem with the atom economy is that we're not taking account catalysts, solvents, or any of this other things that are generated. So the idea is that whenever you have a reaction, you want to get 100% atom economy. God bless her soul. We're trying to do that. But we're just striving for the highest atom economy. So this is one. Let's keep that. The other one was the E factor. So the E factor, it now considers the mass of catalysts, the mass of solvents, and the undesired side products that I've used. So this is like a molecular, the formula of E factor. I'm getting the mass of the waste that I produce, which is like anything but the product that I want. And I divide by the mass of the product that I want. Cool. So I'm striving here for the lowest E factor, right? Because the highest E factor, the most things I have in my reaction, most things that are not my desired product. So let's think about E factor. And I think this was, okay, this is the other activity. Let's hold on to that. Okay. So the problem with the mass, the E factor in the atom economy is that I'm not taking into consideration energy. Oh my God knows what I'm doing with energy. Am I considering toxicity, the environmental impact of my product? No. So how do I deal with that? So chemists created this thing called the life cycle assessment. And it's a very important thing in chemistry metrics for us to actually understand what is the life cycle of my material and what's the impact of this life cycle for human health and the environment. So when I say life cycle, things can get messy. So you can go from the beginning of your material, so it can go from cradle to grave. So when your product is exposed, you can also go from cradle to cradle. So whenever your product is recycled and it comes back and becomes a starting material again. So also you take into consideration energy, raw materials, transportation, everything and every impact of your product from the minute it's generated from the minute it ends. How complicated that sounds? A lot. So that's why the LCA takes more time. And also, like, we have a lot of apps that you can use to actually make LCA, and they calculate things for you. But what I wanted to show you is that, like, energy, global warming potential, ozone depletion, eutrophication, all of these environmental impacts, they are in the LCA, which is really cool. And it's really helpful for you to actually compare what is real and what's not. So as I mentioned, the LCA can be complex, and people, they try to have these 4 stages of LCA to actually make things work. So for example, the first one is to define your system, right? What am I doing the LCA for? Is it to assess the greenness of this chair? So I'm going to take into consideration how much time the chair is used, all of these things. So defining the system, collecting the data. So as I mentioned, there's a lot of like different parameters that you use in the LCA, environmental impact, ozone depletion, and all of these things. So you have to collect this data to construct your little table. And then from that, you get the little table, which can become a big table. And then you can add values to this. And at the end, you kind of interpret the results. So I have this table with numeric values, one for each of the parameters, and I can take into consideration and define if the LCA of if one product is greater than the other. Yes, I knew you would have a question. You're looking at me like a crazy person.
No. I do have a question. Is it like a relative scale? Like, is it a rating of 1 to 10? Is it like in joules? Like, what is it?
So you have a value. It's like it's I don't remember if it's 1 to 10, but like you have a value of like 1, 2, 3, or 4, and you have like this one is better than the other. It's like a comparative. We talk about greener LCA at this point. You're always comparing with something else. Tell Francisco.
Yeah, it's like values like relative to what you're comparing. So if you're comparing two reactions, it's going to tell you like this is better than this one. So
Yeah.
it's not like a universal value.
You have, yeah.
Like an example for global warming potential is just tons of CO2 equivalents. So say you make a green chair versus like a wood stool, we compare it in terms of tons of CO2 equivalent. And for eutrophication, it would be a different unit.
And whenever we complete the table also, we also have like yellow, green, and red values for this comparison. And like this visual helps too in terms of like just having the values to compare. So like at the end you have these. Thank you. I don't know what's happening. Oh, okay. But this is it. So like also having a discussion of the results is also really important in the LCA process to analyze, okay, what can I do better with my process? What I cannot do better? What stage is giving me more problems? Is it the eutrophication? What is going on with my process that I can change? Go, Francisco.
Yeah, so for example, if I'm a chemist and I'm trying to read my reaction, and I change one parameter in my reaction that is greener than the previous one. Can I call my reaction green? Or I should do it else?
It's okay. We're going.
I think that's the better metric to call something green.
It is. But the thing I would say also is like if you don't have the knowledge or how to make an LCA, you go for the easiest thing. You know, but like if you really want something, like you can publish, you want to show that LOI is going to say something too. But but I feel like in my sense, like I feel like if you have the resources to do something green at that point, you can say you're striving for greenness, but you can actually call it green. I hope I made sense. Do I make sense, everybody? And the person on Zoom that was there, random. Okay. So this is as we said, there's a lot of discussion going on. And for those of you who are not familiar with this person, this is Philip Jessup. He's a professor at Queen's University. And to try and educate people about the LCA and what's greener, what's not, he makes a lot of TikTok videos. I'm not on TikTok and I just see his videos because I think they're cool. So I'm not a TikTok person. Go. Okay, thank you, Francisco. It's also on YouTube. So if you're a YouTube person, you can do it. So he talks a lot about which is greener, and he goes to different places and he shows like why one is greener than the other, and you can have fun with comments too because he explains things over there. It's kind of fun. So please check out his TikTok video where Philip is trying the best he can to actually explain LCA to the public. As I said, it can be very complex, but the idea is like to make this like having this comparison makes things easier for people. So also, are people using this question mark? So this is like we have two papers where they the ACS GCI, which is the American Chemical Society Green Chemistry Institute, they made a survey with their companies that they're members and everything, and to see like if people were actually using these metrics in pharmaceutical industry. And they said that over 80% of them are actually using one or more of the green chemistry metrics. 44 are actually implementing the LCA, and the factor is used by 48 companies. So if you want to publish things in terms of green chemistry, having these metrics is also very helpful. As I said, if you cannot do an LCA, having an E factor, comparing something with something that exists already is pretty cool, and you can show like the benefits of your process.
How these
So
metrics are
thank you again. So so actually, for example, the ACS Sustainable Chemistry and Engineering, they whenever you publish with them, they ask like if you're applying the metrics and if you're not, and like which green chemistry metrics you're using. So and I feel like journals are going to start using this more as we strive for more sustainability, and this is going on. Okay. So another
Just one small comment though. There are consulting companies that do this work and they are interested in collaborating with that. collaborating with Green Scale Canada on doing an LCA on my reaction. So they're willing to collaborate, sometimes for free. So if you're interested in doing an LCA, you can potentially contact one of those companies and try to see if actually your research is greener.
Awesome. So also, there's an app called Dozen 2.0. It was created with Millipore Sigma. This is also different attempts for us to evaluate the greenness of our reactions. So this is basically, it gives you a scale from 1 to 100, and 0 is being the most desired. So it also evaluates the greenness of your reagents and also your processes. You just input the data there and it will calculate it for you. So it's a pretty cool platform, and I feel like it's another thing if you want to publish, if you want to share how your green chemistry, how your chemistry is greener or not than the other type of chemistry that's being published out there, and you want to do this comparison. So to conclude, there is no standard thing that we can say, do this, and it's going to work for everybody. But I think this is life. So we have, as I mentioned, green chemistry can be simple, can be complicated. And for us to actually understand this, we need to evaluate different projects, different reactions, different processes, and the metrics that make sense for us and make sense for our work and that we can compare. So atom economy, they can be applied without the need of experimentation. I have a reaction, I can see if it's atom economic or not. The problem is that I don't include solvents, I don't include catalysis and the purification of those. The E factor can help in that sense, but also I have no idea about hazards, energy consumption, and also the water that I'm using in the process. And the LCA can do all these things, but as we mentioned, you have to have collaboration, resources, or even like when I mentioned the life cycle of a product, you can use a shorter life cycle so you can analyze things that make sense in that for the LCA. Other metrics, they're process mass intensity, water usage, carbon footprint, and then you can learn more about them. But the idea is like, just to give you an introduction of how, like, if I want to compare this greenness of my process, how should I do it? So it's just an intro, but it's kind of fun when you do it. Cool. So the activity that I thought it was in the beginning, it's here. So in the Mentimeter, so we have a bunch of different chemical sectors. And just in your opinion, which one you think has the highest value of the E factor? Which one you think is producing the highest amount of waste nowadays? Dun, dun, dun. I'm gonna go there. Okay. All chemicals is good. So I'm gonna give it more time. Okay. We have 3 fine chemicals going. Cool. All right. No one said oil refining. Okay. Cool. All right. So you got it right. The yellow thing, pharmaceutical companies have the highest E factor value. I should get some pom-poms actually to make this more exciting. But yes, they have like multi-step synthesis. Solvents are being generated all the time, and at the end you have your little product in milligrams. So yeah, that's why the pharmaceutical factor is the one with the highest E factor. All good? Okay, cool. So now we have another activity for you, and this is called, which one is the lowest? It's oil refining, actually. It's very optimized for the things it work. Like, it's horrible for the environment, but it works the way it is now. So that's the problem with the factor, see? Okay, so I'll leave you to it right now. We'll have a lot of 15 minutes to come up with this activity, but the idea is, which one is winner? We're going to embrace our Philip Jessups right now, and trying to come up with which one you think is greener in terms of these 2 options. And I'm going to put the Mentimeter here so we can follow up, because this is kind of exciting, and we'll discuss later. and you can talk among yourselves.
Juliana, we have a question from the chat for you.
Tell me.
Giovan
I'm
asks, is there a recommended resource that we can use to start incorporating LCA into our research?
Yes. So I'd say Philip Jessup's one of them, and his papers regarding LCA. I'm not thinking about if there are any textbooks.
There's a handbook of LCA.
There's a handbook and LCA, and also the textbook, and we can send this later as a resource, right, Francisco? But also the book that Andrew oh my God, he wrote about the green chemistry metrics. Andrew Dix also is a good book, and it has LCA there. So yes, we will send them some resources, Chloe, after the workshop, if that helps. If you could give me the thumbs up somewhere, that would be good.
Yeah, thumbs up.
Thank you. Okay, so we have plastic bag. Anyone from Zoom on in person that wants to say why they added plastic bag? We're all shy today. We don't want to talk. I'm looking at you because you had, okay, go ahead.
Significantly less material, like needed in a plastic bag, biggest weighs like maybe 40 bags. And then also the paper bag requires like the actual tree to be grown, it's grown to be chopped, so quite a bit of resources for that.
Yeah. What is the main problem with the plastic bag though? Like in terms of if you think about what we discussed.
Biodegradable. But you can think of biodegradable plastic bag.
So for those people who didn't listen on Zoom, we're discussing like what is the problem with the plastic bag, why people think the plastic bag is better than the paper bag. So I was wondering if anyone on Zoom wants actually to unmute and say which one they chose and why. Is this gonna work? I'm looking at the tower. People are just. Hi guys, you can talk to us too. We're here to listen to you. We're open hearts and open minds.
We have some raised hands. Go ahead. Oh, someone muted and then unmuted and then muted themselves again. Giovanni, if you want to go, feel free.
Okay, can you hear me now?
Yes.
Yeah,
Hi.
okay.
Whatever you
Hello.
want.
Hello,
Hi.
Juliana.
Nice to see you. Hear you.
Yeah, good to see you. Finally meeting you. Anyway, so I'd go with plastic bag because basically because of the resources, like the sources, like it's not renewable, and a lot of plastics will be persistent in the environment. So like the paper bag, you can make that from renewable sources. So that's basically my understanding.
Okay. Thank you so much for sharing and talking to us. Anyone that chose a paper bag wants to say what they wrote. What, oh my God, what I'm saying, why they chose the paper bag.
Juliana, it looked like there were a couple of other Zoom users who wanted to answer. It looks like
Go Zoom users, let's go.
Go on Monday, I'll unmute you.
Okay, good everyone. I chose paper bag because I feel paper bag is more greener in that when it finds itself in the environment, it can easily degrade as opposed to plastic bag. So paper bag is greener compared to plastic bag. Yeah.
Thank you for your input. Awesome. Anyone else?
It's also what we're being told.
Yeah, yeah, exactly. Okay, so I'm gonna show you an LCA thingy of this. So when we look at the plastic bag, it actually outperforms the paper bag in everything but degradation. So, so the idea is like, yeah, the plastic bag is greener if you look at it, but the biggest problem is plastic is very light. We're producing tons and tons amount of plastic every year. It's out of control. The degradation is like, it's small, so it's gonna end up in our environment, and this is it.
It's very durable as well. You need 4 times more material to make paper bag.
4 times more material to do the paper bag. That's what who? Okay. Yeah, the less materials. Oh, good. We have another one. Let's go.
Just a typo here, degradation landfill, they should both be red.
Thank you. So the degradation landfill should both be red. Okay, zoo people. Yes, just FYI. Okay, so another one. Plastic bottle, aluminum can, glass bottle. Which one is greener? And there's a hint to consider recycling. I'm gonna leave this place and let you think. And I'm gonna put the thingy here.
Juliana, I'm also going to mute you while you step away, so when folks chat, it doesn't get loud on our end.
It's muted now. It should be muted now.
Yeah,
Okay.
it wasn't saying so on my end, but yeah, it was quiet. So
Okay.
thank you.
I'm muting. Hello, everyone. Let's do this. Glass bottle is the winner. Who said plastic bottle that wants to speak and say, hey, it's plastic? From here. We don't have glass bottles here. On Zoom, who said, guys, who said glass bottle that wants to speak up and say what they chose plastic bottle?
Again, if anyone wants to answer, raise your hand and I'll unmute you.
Thank you, Chloe.
No problem.
Okay, so let's go to aluminum can. Who said aluminum can that wants to say, I chose it, and that's why? Or I was just browsing through stuff. And then, go ahead.
Aluminum can, because I don't know if it's just what I was supposed to, but like whenever they're showing like recycling and stuff, they always show like people smashing the aluminum and always reusing it. So I think when they recycle it, they are able to extract a lot of the original stuff.
Thank you. So we had someone in the room saying they chose aluminum because of the recycling part, that they see people like smashing up the cans and reusing it for stuff. So thank you so much for your feedback. Anyone else that thought a different thing about aluminum cans that wants to share why they chose it as being the greener? Zoom? No? Okay, okay. Glass bottle. Who chose glass bottle that wants to speak up and say, this is what I think? Thank you.
Yeah, I think the recycling process for a glass bottle is more efficient than for an aluminum can, because I think there's a lot of energy that goes into initially generating the aluminum and also into like the recycling process. Whereas glass, I think it could just be like easy.
Okay. Thank you. Anyone else? Glass bottle. You're nodding to us. Do you want to glass bottle?
I also choose glass bottle, and I know for aluminum cans, they're also coated with plastics on the inside for food safety. So maybe when the aluminum is melted down, there's ventilation of that byproduct. I think glass bottles are something else.
Okay. We're having a glass bottle team here in person. So I want to ask in Zoom, what's the glass bottle team saying? Why they chose glass bottle? If anyone wants to speak up again. Don't want it, it's all good.
Am I allowed to answer?
Yes, Chloe, go ahead.
I would say like when you oh, it looks like someone has a response. Oh, it's Natalie. I was like, oh, someone's hands up. No, so when you recycle a glass bottle, my impression is you can kind of just grind it back into sand and then you use the same sand again to make more glass products. So it's like a very much closed loop process where you can end with the same product you started with and make the same product or a different product at the end of the life cycle if it's recycled properly. But I mean, I don't think that is like a widespread practice for recycling glass. I don't know.
That's what we're here for. I don't know either. Francisco.
Just one comment.
Francisco is gonna say something.
A lot of the answers here are focused on like the end product, right? But we're not really answering from like what's it take to make it. And that's kind of like what the life cycle assessment is trying to.
So Francisco he just like raised the point that we're talking a lot about how the end of this product is going to be, and also in the LCA we talk a lot about how the product's made, so we have to consider these things too. And also I was talking to Jess, and she doesn't want to speak up, but like, do you want to speak up here, what you said to me?
Again,
go in the microphone so people on Zoom can hear. You're gonna present anyway, so I'm doing it. Hi all, this is Jasmine. She's from the Green Chemistry Initiatives too. I don't know the name. It's Green Chemistry McGill group, and she's gonna talk about all the things.
One thing to note with LCA is you kind of have to read it based off of your own like metrics. Like they'll have the different endpoint categories, so they'll have like a category for climate change, and they'll be like, of the compared methods, they'll be like X method is better than Y method, and they'll do that for like upwards, there's like 18 I think in the methods that people traditionally use that you can like assess processes on. But you have to look at like what you like in your research, or like what your goal is for which endpoint you want to consider. So like if you care a lot about the climate change endpoint, maybe that's how you justify which one is greener than the other. But if you care a lot about like eutrophication, if you're doing stuff with like, fertilizers, like obviously that doesn't play into all processes, but you need to look at kind of what's relevant to you. But you also need to be careful when reading LCAs that the people who made them, they'll have inherent biases. So you need to kind of look at what their scope was and what they looked at when you read an LCA, because they're not all directly comparable based on which scenario they're judging. And like what Francisco was saying, you need to consider both like where you source, how it's used, how it's produced, and then its end of life. LCA is very holistic, where it looks at every step, and it considers that like anything that's made is destroyed or reused. So you need to kind of picture that when you, especially in this kind of activity where you're considering which is greener, you need to consider every step along the way and like what goes into those. Yeah.
Thank you. Amazing. So yeah, it can be biased.
So you would be thinking of like, what most are ways?
I was saying, LCAs are loaded with assumptions, and you have to define those. So in that first step, your system, et cetera, like, are we using pristine aluminum or recycled aluminum? That's going to completely change the equation. And so every LCA is really dependent upon this. And you get to very different conclusions based on what you've defined.
Okay, so we're talking about the LCA here in the room of being full of assumptions, and yes, and the discussion is really good, Francisco.
Yeah, so no, I was just gonna say something from what Jasmine said. Here you're thinking about how is it you get the sand that you initially used to make the first glass bottles. In chemistry settings, like, where did I get my chemicals? Were they like sustainably sourced? Or were they legally sourced? Are there people dying because of the mining of like precursors, right? So you're trying to think about all those things.
Okay, so yes, we're talking about, it's very, as we mentioned, complex. You can take a look at different things to show how your green is compared to the others. You made a lot of assumptions because we don't have values for everything. Thank you so much, Tower. Exactly, and all of these things to do the LCA. Okay, are you ready for the answer? Let's do it, pom-poms. Oh, anyone on Zoom wants to say anything? Because I saw faces. The Tower is looking at it. Okay, sorry, we'll keep track in time. Francisco is telling me I have to go. Okay, let's go. So why am I looking at there? Answer. Aluminum, 1. So if you take a look at these parameters, global warming, acid rain, ecotoxicity, and the persistent environment, glass is a no-no. Persisting environment of plastic, we already looked, is a no-no. And aluminum, and aluminum has a good persistent environment, but the human toxicity, as we mentioned, is not good. Are we happy with this result? You're looking at, you're this, what? You have a lot to say, go ahead. You, no, you here. Yes.
Oh.
You're like this result.
No, I was just surprised by glass being persistent in the environment. I mean, it is, but it's just sand, right? Like I don't know, it's kind of negatively persistent. It's
Persistent, it doesn't seem like it'll be harmful.
Yeah.
Yeah.
Just sits there.
That's how the LCA becomes tricky, right? Because it is technically persistent, but it's toxic. It's persistent.
We're talking now about the difference between persistence and toxicity. So toxic persistence. We can go forever here, I feel. But then, like, the idea is to show you it's not simple as it looks. There's a bunch of assumptions. People are still discussing it here, so I feel like we could take forever. I think the goal is achieved to show you that it can get complicated depending on what we're doing and the assumptions we're making and what we're trying to look at. So that's why these 4 steps, these 4 stages, and having identified the system we're working on is very important for the LCA. All good? And everyone's gonna go to TikTok today and do this. Cool. So guides for greener chemistry. We're going to talk a little bit about solvents and all of the things that we can do to make our reactions greener. So why is this thing here? Great. So solvents, we use them every day. Dichloromethane, perfect, does everything we want it to do, right? So the problem with solvents is that they give us all the things we do. They make our job so much easier. I used to have a little reactor. I tried to clean it with everything I could. Dichloromethane, best thing ever. So the problem with the solvents is that they can release volatile organic compounds. They can form low level ozone in smog. They have a lot of adverse effects. Can make like your skin, corrosion. They can having problems in your eyes. All of these hazards. They are flammable. So if something happens in the lab, I remember that I used to work in a lab in Brazil. We didn't have a place to put dichloromethane. It was there all the time in the heat. Great. So if something happens, it was not going to be good. So this is a problem with the organic solvents that we have. And people have been created different alternatives for those. So these are a couple of examples of solvents that are being incorporated to substitute other solvents. So we have ethyl lactate, gamma valerolactone. We have 2-methyl tetrahydrofuran, which is obtained from renewable sources, and the CPME. Not going to say this big name, but also, and these are the best things that they can do and why people are choosing them. Another solvent that is being used is called styrene. It has a weird structure, you can see there, and it's a good replacement for DMF and NMB. So what I'll say to you is that people are trying to get different solvents and use alternative solvents also because of regulations, and also like people are noticing the effects that they have in human health and the environment, and they want to do something about it instead of giving your reactor a bath of dichloromethane. So to do so and help us, we have different solvent guides. So these solvent guides, they were built taking into consideration all of these hazards we spoke. So flammability, occupational hazard, damage to aquatic life, all of these things. So they created a list of how you, based on these things, we can choose solvent alternatives and actually implement them in our research. Just like we're talking about LCA here, different solvent guides can have different numbers. A solvent that's green in one solvent guide can be yellow in another one. And it also depends on the things, the assumptions, the things we're doing, what we care or what we don't care. So here are a couple of examples of solvent guides, the GSK, also one that's released by Pfizer, and the one that I think is the most comprehensive one, which is the Chem21. So the Chem21, I'm just going to show you how these solvent guides work. So as you can see, you have this range of things, and then you can substitute one of your solvents for the other. All things you can consider here are also costs. Sometimes it's hard to, depending on the resources that you have in the lab, to have a specific solvent. But this is the beginning of thinking how you can replace your solvents and make your reactions winner by simply switching one thing that you're using in one of your reactions. So these are examples. This table over here, it's part of the Chem21 and then includes like greener solvents and their hazards and their safety and the score sheets. I'm taking a time for you to, your face is killing me. He has his mouth open right now. But I'm taking some time. All good? Does it look okay? So the problem with water is also like after you use it, right? Exactly. So the recyclability of water is not really recyclable. So there's all of these things that are included.
So that's one of the things that Phil Jessup likes to hammer on. It's like, sure, you change the water green, but like you need to really distill the water to reuse it.
It's going to
So
take
if you're in a closed
forever.
system, water is probably not green. So
Yeah.
like water is gonna like end up in the environment, sure. That's
We're talking about water being not very green in terms of recyclability and how like the process to recycle water is not very green.
I think to that point, there's an LCA of ethanol versus bioethanol, and the bioethanol really suffers because of that distillation study.
And we're talking about ethanol, bioethanol, and the LCA suffering from this step of recycling. Yes, this is all the things we're talking about. All good. So these are the solvent guides. And to try and help people do reader choices, we released this solvent guide together with Milk Four Sigma. This is a magnet, and we can order some from the website if you guys want to put them on your walls or your lab. It's basically like, I'm doing this reaction. I want to try something different. I want to try something greener. What can I do? What can I choose? So this is the list of solvents, greener solvents that you can apply. And we have at the top, there is no universal approach to solvent selection. You know, it depends on what you're doing and all the things. Are you considering recycling what we're doing with the solvent? So these are things and steps that we need to take into account when we are doing this. Okay. So we have another activity, which is called Which Solvent Screener. So I'm going to take you a while to do this. So we have here this graphic, and it has a bunch of different solvents. And the idea is like, pick 3 solvents, write them down, the ones you think are green. And then I'm going to show you a graphic with the ones that are green. And then we're going to see how many you got right. And I'm going to leave, and I'm going to mute, and I'm going to give you some time to look at this thingy. I didn't mute. Hello, and we are back. Did you have some time? All good? Did you write down the solvents you think? Are we ready to see the results? Okay, I'm gonna go. Okay. So I see some happy faces, some sad faces. Okay, so how many did you guess correctly? We want to know. Tell us in Mentimeter how many of the solvents that you pick. Okay. Cool. No one got 0, so I think we got all acetone there. And it's acetate. Good job, person of 3 out of 3. Cool. Nice, everyone. Thank you. So are we ready for another round of this one? Because we have more solvents for you. This one should be easier. I don't know. Let's go. Okay. So great job. We're doing this. We're choosing better solvents. Okay, another one. Which of these ones you think are green? Write down. Are we ready? I'm Debbie. Ready? Let's go. Okay, I'm gonna show you the answers. You better be ready for this, everyone. Dun, dun, dun. Okay, your faces are killing me right now. Does anyone want to share what they're thinking at this moment? No? Yeah? All good? Let me check Mentimeter to see how many you've got. Okay. Oh, no, this is part 1. Part 2. Oh, look at that, 3 out of 3. Yes. We are better in this one. Awesome. Great job. Okay. All good for solvents? Do you know now where to look for if we want to replace things? Cool. Go, Francisco.
One thing that always surprises me from this plots is that if you go back,
Okay.
is that the green replacements are always in a certain area of that plot.
Mhm.
Low polarity, low basis, there's no really green replacements, which is problematic for some things that need those solids, no replacements. Research opportunity.
I'm gonna try to catch all of that. So Francisco said how interesting it is that in the graphic, like all of the replacements, they're kind of in the same area. Is there anything else that I missed? You said some, yes.
We're missing green replacement.
And we're missing green replacements, and then people have to search. Yes, it's an opportunity for people to research those. I translated correctly. Okay. All good. So great. Check out the solvent guides later. You see that some of them, they have different things. But also if you want a solvent magnet, we'd be happy to send some to you if you want to reach out to us, and you can put everywhere in your labs and you're everywhere in your life. I have one in my fridge, in my house. Anyways, let's go. Platforms for greener chemistry. Correct. So we're going to talk a little bit, we're talking about hazards, and we're talking about how green chemistry can help us to get materials and reagents that are less harmful to human health and the environment. One thing that we don't think about it too much, and I wasn't taught how to do so in my undergrad, is about toxicology, toxicity, and all of these things. So toxicology is very important. It studies the effects of chemicals on human health, on living organisms. And as I said, it's very important for us to know how to design chemicals that are less harmful. So two parameters that are really important in terms of whenever talking about toxicology and toxicity is the LD50 and LC50. And I'm going to show you a little bit how you can use these parameters later. But the LD50 is the dose, that's why it's LD, at which 50% of a test group are killed. So, okay, I'm gonna get a little bit sad here, but like in terms of, it's expressed in terms of milligrams of chemicals by the kilograms of testing subject. And we also have the concentration in air or water that kills 50% of this group. So we have the results in ppm or in milligrams per meter. In terms of toxicity, so the lower the LD and LC50 your material, the more toxic it is, and the higher this number is not very toxic. So why am I talking about this? Great question. So how I learned about materials and safety is that my PhD supervisor, she always was talking to us in terms of when you're using something in the lab, go check the SDS sheet. Go to check the safety data sheet. This is available, this is there, we can find it anytime. So for example, I was talking about how dichloromethane being the best solvent ever, carcinogenic, we don't like that. So you can find all of these things if in the safety data sheet of your material. So for example, you can have this hazard statement of like what the material, why is it bad for you? And also this value that I talked to you about of LC50, LD50, you can also find them at the SDS sheet and have an idea of the toxicity of the chemical that you're using. Also, if something happens, if an accident happens, you know what to do with this material, which is also very important. I know we're always positive, but things happen in our lives. So it's good to have an idea of what we can do. All good? So now I'm going to talk about going to another completely different section where we're talking about how you can try to do your reaction greener in terms of systems and what you're doing in platforms. So have you ever heard about sonochemistry? Have you ever used sonochemistry for your reactions? So the idea is that you have an ultrasound, and sonochemistry is based on this phenomenon called cavitation. So you have sound waves, and they have this compression expansion cycles, and they form bubbles. And at some point, this bubble implodes, not making this sound, I'm sorry. And this generates high temperatures, like 5,000 degrees Celsius, and a lot of pressure. And this is able to create reactions and makes increase reaction rates, reduce the waste production, and also lower the energy requirement for your reactions. Francisco.
Just go to Sonic here.
It's a sonicator. So you have two types of sonic chemistry, for example, that you can make. I don't know if you noticed, but you can have the direct sonicator, which is one that contains a probe, and you can actually immerse the probe in your reaction, or you can do reactions in the ultrasound bath. So it's not only to clean stuff, you can actually do reactions with it, which is really cool. All good? Another one that I like to talk to you about, I love this, mechanochemistry. So I think mechanochemistry is the future. There's a lot of things for us to study. So we're talking about solvents a lot of the times. But if I can't change, if I can replace my solvent, can I do my reaction solid state? Mechanochemistry helps you. So the idea is that we're going to have stirrers. We're going to have ball mills instead of stirrers. We're going to have beakers and flasks replaced by jars. So this is an example of a vibrational ore called shaker mill. And the idea is that you're going to put your products and your automated, your little ball over there, and you're going to shake this vessel and with the intensity of the milling that you want to promote chemical reactions. So why mechanochemistry is so cool? We're eliminating solvents. So it's also less energy and time intensive. You can remove completely solvents, or you can use just a tiny bit. You have less hard disease chemical synthesis because you use that. And also you don't depend on actually having to dissolve your solvent to promote this chemical reaction. So if you haven't had contact with mechanochemistry, I suggest you to do so. It's an increasing platform, and people are trying to do more reactions with it to do the things we do in life. Cool. So now that we've heard all about this, we have a huge activity. And I think the point here is to think about a process or about a reaction that you do in the lab currently. If you don't have one, don't worry. We'll give you some examples. But the idea is, think about this reaction. Do I have any hazards associated with my starting materials? Do I have any hazards associated with the process? What are the solvents that I'm using? Are they hazardous solvents? Can I replace them? Can I use bio-based starting materials instead? Can I use catalysts instead of using 50, 100 millimole of moles of something else? Can I put this in a ball mill? Like, how is it? Can I use a sonicator for this? So all of these things we talked about, I invite you to think about it right now in terms of your research. If you don't have one, we'll give you an example, and then try to think how you make this reaction leaner and how you could do that. So I'll give you plenty of time to do so, and then we're gonna come back and discuss the things you came up with. But this is your time, and also we'll be around if you have questions. If you don't have ideas, or if you have ideas, please feel free to talk to each other. So if you can get into groups, that would be perfect. I don't know how to count. I don't know how many people are here that we can separate the groups with. But if you get in groups and just start discussion, if you don't want to talk to anyone else and just me, that's fine too. So in Zoom, we're gonna go to breakout rooms and do these things. So if you have any questions, please let us know. But this is your time to think and to practice green chemistry and start deciding, putting in the pencil in the paper of how we can make things better. Sounds good?
How much time do you have?
We have until 1 p.m. Oh my goodness, that's a lot of time. So let's go until 12:35. We'll go until 12:35 to do that. All good? Thank you. Let's go.
Hi, everyone on Zoom. I'm setting you up right now, so just give me 1 second.
Thank you, Chloe. Yes, and if you have any questions, you can send us on Zoom too, and I can check them, and we can do things.
So everyone, I've randomized the rooms. I'm gonna open them now. You should get a notification or just get pulled into those automatically. Okay, so they're open now if you can join.
I hope we're almost there. Zoom people, thank you so much for staying with us all of the time. People in the room, thank you so much. We're just gonna go through some resources if you want to apply the things you've done here today. If you want to make a change, how to do so. I'm gonna invite all of you right now on Zoom and in person to this. So this is called the Green Chemistry Teaching and Learning Community. Beyond Benign created this platform with the ACS Green Chemistry Institute. It was launched recently, and it's basically a platform where the green chemistry community is, and the idea is to have all of us there so we can share resources, network, communicate. We have forums, so we have job opportunities too. So we have everything. Yeah, thank you for scanning the QR code, everyone. So just please sign in and you have these opportunities. Everything is free, everything is there, all the resources are available to you. And the idea is to connect this community so we can continue to make change together. So please sign up for the GCTLC. Also, John mentioned, Jasmine, did you mention the Green Chemistry Commitment? I forgot. So John mentioned the Green Chemistry Commitment is a program that I'm thrilled to manage at Beyond Benign. The idea is that we're going to support institutions around the world to insert green chemistry education, their teaching practice. Here at the University of Toronto, you're very lucky. You have a great education system. You're learning about green chemistry. You have a green chemistry group that's organizing this workshop. I didn't have this opportunity whenever I was in Brazil. I had to go through and find things on my own. So let's go. What I was going with that. But yeah, so this is the Green Chemistry Commitment Program. As John mentioned, we grew a lot. We have 161 signers currently. And the idea is that these institutions are not only adding green chemistry in their curriculum, but also like in terms of a broader sustainability in their institutions. So like inviting people to participate and other faculty, other students, and really creating this movement of change. So we just published a paper about the GCC, accepted as of March 4th, 2020. I got the edits yesterday. So like if you want to check out more about the history of the Green Chemistry Commitment Program, I have the DOI. I can also share this with you. But the idea, we just published this to make sure that we write in history about the Green Chemistry Commitment, the impact and how green chemistry education is catalyzing the change for a sustainable future. So also, if you're students here on Zoom, here University of Toronto, you're already signers, but like if you know any other colleagues in different institutions in Canada that are not participating in the Green Chemistry Commitment Program, please invite them to participate and be part of this change with you. We need 2 signatures, 1 administrator, department chair, and 1 person that's going to be the contact. And then we start supporting these institutions to do so. So there's a QR code for you if you want to learn more. My email is over there too, by the way, if you want to email me and talk about anything. And I'm going to pass this to Jess because she was going to say this earlier and said, say it at the end. So thank you.
I just wanted to highlight some other resources that are like out there that are kind of cool, both resources that like are things you could sign up in or like and get like educational or useful like things that you could use, but also some that are for funding or like kind of signs of industrial relevance. So I'm just going to be a bit of that also. So first I want to talk about My Green Lab. So they're a nonprofit, but their goal is basically to kind of create systems to like grade yourself on sustainability and like kind of help educate people and provide resources to like make changes in your work. And they have like 3 flagship programs that I just wanted to highlight. So the first is the My Green Lab certification. So it's basically like a little like a quiz you will fill out, and like you'll look at your workplace and like the work you do as a team, and you'll be able to evaluate yourself on these 14 categories. And you're able to kind of look at where in what you're doing you could improve sustainably. So basically through this program, you'll like get like a ranking. So they have different like levels of like, I think it's like bronze, silver, gold, like platinum. And they'll work with you to both fill it, like once you fill it out, they'll like work with you to see where you could improve, and they'll like make suggestions and ways to do that. One thing that's cool about this system is it's internationally recognized. So if you're like in a lab and your professor is really into doing green chemistry or sustainability and they want to be like recognized and accredited for that, this is a cool way to kind of put like that kind of stamp on what you're doing. They also, if you can't get your lab involved, but you want to be involved and maybe one day help your lab get involved, they have an ambassador program where basically it's like a free online learning program where they'll provide resources on things that you can change in your work. And it also gives you access to their ambassador network, which allows you to kind of interact with people around the world and kind of share ideas on ways to like reduce waste, how to build community, how to reduce like energy consumption, and also like water usage and waste like that. They also have one that's more industry focused, which is their ACT program, where it's kind of based on the idea of accountability, consistency, and transparency. And it's basically a database of hazards and environmental assessments and impact analysis that companies can use so that it's easier to interface between scientists and like procurement teams. As in industry, a lot of the issue is there's a disconnect, I think, in those kinds of groups. Like they'll have like hundreds of people on procurement, but then have like a 10-person sustainability team. So they've created this program as a way to kind of, it does provide like a number at the end, but basically it's to help people in procurement make more sustainable choices. On industry as well, but also funding, I wanted to highlight the ACS Pharmaceutical Roundtable. It's basically all of the biggest pharma companies you could ever think of, and they get together and they it's not under the table, but it's basically like, we'll show you what we have, and we won't take it out of this room, from what I understand. So it's so they can kind of communicate together and help move the industry of pharma into a more sustainable place without kind of the barriers that you would expect of like trademarks, like business jumbo, basically. But one thing that's really cool about the ACS Pharma Roundtable is that they actually provide grants, and they're very generous with these grants. And it's not just for people doing pharma or drug discovery. Like at McGill last year, Bruce Armstrong recently got one, and he does mostly like uses like metals and does polymers. So it's not just like drug synthesis people. They're like basically interested in anyone developing any chemistry related to these like categories I've listed here. Another example at McGill, there's like I think it's like solid state peptide synthesis. They're using they're using sonochemistry to produce to synthesize peptides. So they could use for stuff like that. So it doesn't have to just be like what you would expect a pharmaceutical roundtable would be interested in. Yeah. So it's like, if you like think there's a project idea you have, or like your PI might be interested, obviously like it's a cool route to go. There is also, I think this is more based obviously in the States, but the EPA does a similar thing where they highlight companies every year doing innovation. So this year, these are their groups, and they've given out, and every year they do these, and they put one for academics. So they will focus on like award one research lab. Last year, it was one at the University of Michigan for finding food waste for batteries, which is really interesting. And they also last year awarded Solugen, which is a company based out of Texas, where they use a combination of catalytic, like using catalysts and then enzymes to take food waste, or like not food waste, but biomass, and transform it into fine chemicals that can replace petroleum feedstocks, which is cool. So yeah. You also asked me to highlight Change Chemistry, which used to be known as GC3, and it's kind of like the Pharma Roundtable, except for all companies. So it's basically a joint network of like over 100 companies, I think 117, but it's like actual companies you've heard of. Like there's a mix obviously of like science startups, but there'll be like, it's also like Apple, Sephora, like Walmart, like basically it's a way to help accelerate, like the purpose of the program is to accelerate commercialization, adoption, and like scaling up green chemistry and sustainable solutions across sectors. And it helps to like, these companies are all in it so that they can work together and also get like that information to help them with their procurement mostly. And I wanted to highlight a case study for Apple. So Apple is actually weirdly into sustainability. I mean, it's not weird, but like they're much more upfront with it than you would think they would be, considering the scale of their company. So Change Chemistry has a case study on Apple looking at their Safer Alternatives program for specifically, I think, cleaners. And basically they were looking at all of the chemicals that they use in their production, identifying the hazards, and then trying to find solutions, but like throughout their whole supply chain and all of their like production facilities. They even worked with this other, it's like a third-party nonprofit, I believe, called Clean Production Action, where they helped them develop a criteria for safer cleaners, and then that was reflected in a tool that's similar to, I think, LCA, but for like business people, where I think it's probably more of a black box on their side, but they'll be able to see the results of that kind of assessment, and then with their R&D, they're able to like help think of new solutions to swap out things, which is cool. And I will bring back Ju, as that is what I had, and I will go through.
So this was very fast. Yeah, so it's over. I just wanted to say thank you so much for being here. Thank you, people in Zoom, for being here today. I hope this was a great experience to all of you. And this is your QR code for our newsletter. So if you want to learn more about Beyond Benign, what we're doing, interact with us. If you want to be just like Just Jazz and be advocating for the nonprofit for green chemistry, we would love to have you. We're everywhere, we're remote. So please reach out to us. And these are all of some of the partners that help us to do our work. So thanks to them too. Thanks to all of you. That was amazing to me. I hope it was great to you too. I hope we can go and do some things and change together. So thank you for bearing up with me. Yay! And I leave your oil people that organize the
Thanks everyone for coming. I hope that you were able to find learn something useful today that you can go and tell other people or apply it in your research. Yeah, stay in touch. Join the GCI if you're interested. We're always looking for initiatives as well. Since I'm graduating at the end of the summer, so it's going to be a turnover. So if you're interested in continuing this sustainable and green chemistry movement, please join us. We need more people. We need more voices. So yeah.
Thanks for coming out, and also we'll send a feedback form if people can. This was the first time we've done this.
Yep.
So people can let us know if you want more of something, or a new activity or whatever. That you tell.
And this was recorded, so we will upload it to our YouTube channel. So please share and
like and subscribe.
Like and subscribe. And we'll see you next year.
Yay.
Or the symposium.